Good morning and thank you for joining today's technical breakfast briefing. My name is Pradap Rajagopal. I lead a global solutions architecture team at Sienna focused on our routing and switching solutions. Welcome for those that are attending this session for the first time. Just as a recap, these are intended to provide education on a variety of relevant IP topics for the ANZ community. They are technical in nature. We do have a recording of part one that we did last month for those who missed it. So please do reach out if you're interested in viewing that recording. And just as a reminder, we do need to let you know that we are recording today's session. So today, we again have William Brioski, Routing and Switching Solutions Architect, who will continue the discussion on SRv6, the state of the art in 2023. This is the second part of the SRv6 series. Please do ask questions throughout the session using the Q&A function. We'll answer the questions either directly on the call or follow up after the call offline if we don't have time. With that, without any further ado, I will pass over to William because we do have a lot of material to cover today. And William, over to you.
Thanks, Pradap. Good morning, everyone. Once again, thanks for joining. As Pradap correctly says, we have plenty of material to run through today. So just reminded on the first webinar of this series, we talked about what the SRv6 is really and why it may be relevant for you. And today we'll start a bit of a deep dive, more looking at how it looks like and how it works operationally. So the assumption is that everyone is familiar with the general concepts of segment routing, probably with SRMPLS. So the focus for today is specifically on SRv6. Occasionally, I'll make some comparisons to SRMPLS that may help clarify the concepts. So what we'll cover today is anatomies of how SRv6 segment identifiers, and headers look like. What are the operations of segments and how they manifest themselves in SRv6. And in particular, in the case of traffic engineering, which is basically source routing, or in case of best effort. And we'll touch on the topic of header optimization, header compression. We'll talk a lot more about that in particular in the next webinar of the series. So starting from how does a SRv6 segment ID, a SID, look like? So it takes the form of an IPv6 128-bit address, and it's made up of three fields. The first one is called the locator, identifies a node, a router in the SRv6 domain. And then there is the function that identifies either a topological element, could be the node itself, could be an interface for an adjacency SID and so on, could identify a VPN context within the node, or could identify a more advanced function. And optionally, there may be an argument to the function to specify how the function should operate. An example is identify an Ethernet segment in an eVPN context. Now, the total size of the three fields is 128 bits. The respective size is a matter of design choice. Common choices that we see are having the locator taking 64 bits, and therefore having a /24 concept, and the remainder of 64 bits are available for function and argument. Now, I should mention that the locator is further logically divided in what's called the SID block, SRv6 SID block, which often takes the size of 48 bits, and then a node identifier, which obviously would take the remainder 16. So once again, the length of each of these fields is not fixed, and if your network reality requires, say, more nodes, or a longer SID block, that's absolutely doable. So how does the allocation work for, so how does one come up with an SRv6 SID? So it all starts from the delegation that a service provider or a large network would obtain either directly from a regional registry or from the upstream service provider. So in the case of a service provider, typically you would get a /32 delegation. So looking in the middle of the slide, that 2001 DB8. So that's the IPv6 address space assigned to your organization for everything. So that's private use, internet use, and SRv6 as well. So what you would do out of that, you take a small portion of it. In the example, being a /48 is 165,000 of the total address space available, and use that as the seed block. So all the SRv6 seeds would sit within this supernet, within this /48. That consumes a very small portion of the address space, but at the same time it's still extremely large. So that's usually the case in the IPv6 world. You can take a small portion of it and it's still extremely large in terms of what you can do within it. Now the next step, so that the seed block is valid, is used for the whole network, for the whole SRv6 domain. The next step is the locator, which identifies one node. So that's assigned for each router, for each node within the domain. So again, hierarchically, we still have the physical relation, the block. So the first 48 bits are fixed, and then in this example, the next 16 bits are used to identify node X, A, B, C, D. So that leaves us with a /64. And before we move further down, just compare these to how seeds are assigned in SRMPLS world. So in that case, you start from an sRGB. That again is a design choice, and you have to think very carefully, plan ahead, what will eventually end up in that sRGB. And if you didn't plan correctly, then you're in trouble. Now in the SRv6 world, it's a lot more flexible or less restrictive. You take a /48 for the seed block. If that turns out not to be sufficient, you can always allocate a second block. There's no restriction on that. Or the scenario where maybe you're merging two networks. Again, with SRMPLS, you may end up with incompatible sRGBs, or maybe even worse, with compatible sRGBs, so that you end up with a conflicting node seeds. In SRv6, you start from a public delegation, so it's unique, globally unique, so there's no risk of conflict. And if you merge the networks, the first step is simply, exchange a /32 or the /48 route, and you already have communication happening. So going down to the next level of detail, so within each router, within each node, you have that /64 address space, and that is used to assign all the topological and functional segment identifiers. So things like the node seed, in the example, just take the 0, so it's the same as the locator in terms of number. That's not mandatory, could be a different assignment, of course. The other examples here are the adjacency seeds that identify each interface. For example, the 100, 101 in each router, in this case, identify port 1 and port 2 respectively. And then you could assign other segment IDs for PRS, Layer 2 VPNs, EVPN, and so on. And all of that would sit within the locator, within the /64 for each router. Now, again, a comparison to SRMPLS. In the SRv6 seed, there is often more information than in an individual SRMPLS seed or label. Typically, you would have the equivalent of the node seed plus the equivalent of a service label or adjacency seed, and all of that is combined in a single SRv6 seed. So that's how the seed, the address, looks like. The next thing we look at is how does the SRv6 header concept looks like. So we start from the IPv6 header, and since the very beginning, SRv6 allowed for extension headers. And in this case, we will be using extension header type 43, which is the routing extension header. And again, that existed for quite a while. There are several subtypes of routing header, some of which are sold and eventually became deprecated. Now, the one that we use for SRv6 is type 4, segment routing header, or SRh. So the combination of the IPv6 header and the SRv6 and the SRh extension, that's what we call the SRv6 header. We touched briefly on this in the first webinar as well. Now, the next thing we look at is how the field in the IPv6 and SRh headers operate together in SRv6. So starting from, we know the segment is represented by an IPv6 address, 128-bit seed. If we have an SR policy, a whole path with several segments, segment IDs, those are stored in the SRh extension in the reverse order. So the first segment in the path is the last segment in the list. That can be a little bit confusing, but basically at the bottom of the table you have the first segment, and then gradually coming up you have the subsequent segments, and the top of the table is the final, it is the last segment. Then the first segment is also pointed as part of the SRh header by a specific field, which is called, confusingly enough, last entry. And I hope the diagram helps visualizing that. There is another field which is called segments left, and that gets updated hop by hop, as each segment is completed, and it moves up. So it will start from the bottom of the table and gradually progress up to the top of the table to the last segment. The currently active segment, which was pointed by the segments left field, is also copied into the IPv6 header, and that's very important because that allows forwarding within the scope of a segment just by looking at the IPv6 header without having to inspect the SRh at all, which was 0.6. The next few slides zoom in on what are the basic segment operations, and we'll run through a couple of examples for traffic engineering as in the best example case. So the basic segment operations in SRv6 are the same as in any segment routing option. So there's a comparison here with the SRMPLS, but basically the push operation is done typically at the source node. So the originating node pushes one or more segments. In SRv6, it means populate the SRh, create and populate the SRh. Now, the continue operation is what happens on a transit node where the segment is not complete. So if the destination of the segment is further down, then the operation is simply route according to the IPv6 destination. No more, no less. Now, what that means implicitly is you can have portions of your network that are not SRv6 enabled, they're purely IPv6 routers, and those are capable of performing implicitly the continue operation. Now, what they cannot do is the push, so your ingress edge must be SRv6 enabled. And also an IPv6 router without SRv6 could not perform the next operation. So next means you reach the end of the segment, the target node of that segment. So process the next segment. So move up the pointer in the SRh, copy the next segment ID into the destination address and route accordingly. Corner case, this could be the final segment. Then if there are no more segments, the next operation is process according to the meaning of that segment ID on the router itself. And we will look at that in detail in the next webinar. Now, the examples, first examples is a traffic engineering case. So south routing decision from node A through a number of transit nodes, node B, node C, on node C, we are choosing to take the lower link using an adjacency seed, and finally reaching the destination node D, and also will identify a VPN context on node D. So VPN identified 42. So what we populate, what node A populates is a IPv6 header with destination pointing to the end of the first segment, which is B, and the segment routing header is populated with the sequence. So reading right to left, the first hop is B, the second hop is C, interface 1002, and the final hop is D, VPN number 42, and all of that is encoded in 3 SRv6 seeds. So just zooming in into the IPv6 and SRH, you can see how the fields are populated. So segments left points to the bottom of the table, item number 2, which is the first hop, B00, and that's also copied in the destination address. So that is the manifest, the push operation. Now the next operation will be a next. So the end of the segment has been reached. It was B was the end of the first segment. So what happens on the headers is segment left is updated to point to element number 1 in the table. So which is C1002, which is then copied into the destination address. And then again, the next what node B does next is perform routing based on that destination address. So send the traffic to the logical subnet C/64, which points to node C. Now again, the activity on node C is the operation is a next operation, because that is node C is the end of that second segment. Again, similar operation on the various headers on the SRh segments left is updated to point to element 0, which is the D010042, which is also copied on the destination address. Now the peculiarity here is because the incoming segment into node C was an adjacency specification, that basically restricts how the forwarding from C to D happens. So C will perform a forwarding to node D, but it's only able to use a subset of the potential paths, and in particular subsets identified by the adjacency seed, the meaning of which we assume is using the lower link rather than the upper link. So the final step is the traffic is received, the packet is received at node D. Again, this is from segment point of view, for segment point of view, this is a next operation, but because it is the last segment, there's no more updates to be done on the headers. It means now this is the actual end of the path. Look at the value of the segment ID and interpret it according to the local meaning of that particular ID. In this case, we assume it means associate the packet with a VPN, or VPN number 42, and then do a further inspection of the payload and perform the routing accordingly in that routing context. Now, the next example is similar, but using a best effort case. So in this case, there's only one segment, and this is a segment that goes from A to D. It's the same as the last segment in the previous example. So it's D142 identified, node D and particular VPN. Node A in this case is not adding a specification of what path the traffic should follow. So from A to D, it will follow the IGP, lowest cost path, which we assume in this case goes through nodes B and C. As we were saying before, node B and C in this case don't need to be SRv6 enabled. They only need to be able to do IPv6 routing. So what the SRH looks like in this case, it's much smaller. There's only one segment in the list. Obviously, the pointers, first segment and segments left, point to the only segment possible. The destination address contains the same the same value. So this is the push operation coming out of node A. On the transit nodes, B, C, and so on, there's no change on the SRH, obviously. The SRH is not even inspected because the destination address doesn't match the transit node. So all that happens is the continue operation, which once again is IPv6 routing. So that's the same on node D, and we're assuming there is an ECMP arrangement here, so could take either link. And finally, get to the to node D. At this point, it's the end of the segment. It's the next operation. It's exactly the same as I was saying before. So decapsulate and treat as a VPN. Okay. Now, what you may have noticed in this particular case for the best effort is that the SRH wasn't taking a particularly useful purpose, given there was a single segment and all the information was already included in the destination address. Now, that has been actually observed, and it's the simplest case of header optimization, right? If in the best effort case, it is possible to just get rid of the SRH completely. So that's in general technique called the reduced SRH, which removes the first segment of the list because it's already well known. But it's only really useful to reduce the size of the packet meaningfully in the best effort case. So in this case, the SRH header is completely unnecessary, it can be removed, and basically the packet can just be, the push operation could just generate a pure IPv6 packet rather than IPv6 plus SRH. So it's a simple optimization for your best effort traffic. Now, the more interesting case is more in general for the traffic engineering case. And let's remember that traffic engineering is used in segment routing often implicitly. For example, TI-LFA uses traffic engineering under the hood, uses source routed paths. Micro-loop avoidance also uses segment routed, source routed traffic engineering paths under the hood. So even if you think you don't need explicit traffic engineering, it is going to happen anyway. As soon as you have your best effort network with TI-LFA enabled, under the hood there is some traffic engineering. So it's still important to have an efficient way of transporting source routed packets. So the technique that has been developed over the last few years is goes under the general name of compressed SID. There's a few different flavors, but I'll get into that in a moment. The general observation is looking again at the format of the SID of an SRv6 SID. There is the locator portion that can be divided into a block portion and a node identifier portion. Now, the locator block portion doesn't change. It's assigned for an SRv6 domain, and in most cases, it doesn't change. So you would have a sequence of segment IDs that would all have the same block portion. So it's, maybe we can get away without repeating that. We use it once, but after that, we don't need to repeat it again. Obviously, the node and the function in particular are the components, the elements that keep changing. Each segment will have unique values here. Now, the argument is most often not used and populated with zeros. So we may as well just get rid of it when it's not really necessary. So that's the basic idea. Avoid repeating information that is redundant, and avoid including information that is empty. Fields are empty with information. So that leaves us basically with the locator node portion and the function portion. And again, that can be subdivided arbitrarily in terms of number of bits. And typically, the goal is to try and make that combination somewhere between 16 and 32 bits. Now, the other idea behind all the compressed SID methods is then try to put several of those locator node and function components into a single 128-bit container. and therefore obtaining much smaller headers. Looking at the landscape in terms of standardization, so the SRv6 header can be uncompressed on the left, so that's fully standardized in the RFC. That's what we've been looking at in the examples today. It's called typically called classical SID. It's not an official name, but that's what it's usually called. On the right, you see what's happening on the compressed SID. So there used to be two competing sets of drafts in the ITF. More recently, the two sets of drafts have been unified under the compressed SRv6 segment list encoding SRh ITF draft. So that is a fairly mature draft, although the latest update is only from a few days ago, but it is fairly mature. It includes a list of current implementations. Now the political compromise here is that both of the original drafts have been incorporated into the now common draft. So the first set used to be called microSID, and now it's incorporated under the name of next CSID. And the other set was called generalized SRv6 or generalized SID, and it's incorporated under the name of replace CSID. So both are included in the draft, but they are two different ways of operation, and different vendors at this stage typically only implement one or the other. So we'll see what the future brings. The split is kind of on the geopolitical lines mostly. So the Western vendor tend to implement mostly the next CSID, and the Chinese area vendors tend to implement more the replace CSID. But we'll see what happens at maturity. To the top of the other, we will dive into both options in the next webinar. So just as a recap of what we looked at today, we looked at SRv6 SID and address space, the various components. We looked at the operations, segment operations. We looked at traffic engineering and how it manifests in the uncompressed SRv6 headers. And we started touching on the concept of header optimization. Now, what we would cover next time is the network programming. So that includes things like endpoint behavior, headend behavior, how they are encoded. And that's also a necessary premise to dive further into the two compressed SID flavors, because they're defined in terms of the network programming behaviors. And if time allows, we may start looking at interworking between MPLS, SRMPLS, or traditional MPLS, and SRv6 in different parts of your network. So thanks for the attention so far. We have 1 minute if there is time for a quick question, maybe.
There's a couple that have come through. Probably the one that's most interesting here. It seems like the VPN label is encoded in the SRH. Is that the case? And if so, does that mean we now no longer need a VPN label for SRv6?
That's basically correct, and that's one of the fundamental differences between working with MPLS and working with SRv6. So that's part of why the whole adoption of SRv6 by the vendor, if you remember the conversation last time, took a little while. It is a big change, but yet it can be encoded directly into the SRH, or anyway into the SRv6 SID.
Excellent. Yeah, that was a really good question. I think we're at the top of the hour. There's a couple of other questions more specifically about Siena's implementation, but that's not really the intent of these sessions. So we'll follow up on those questions offline. So thank you everyone for joining. If you do have any more questions, please do send them through. We're both available on LinkedIn. You can connect with us that way. And for those that did ask questions, we will make sure we get an answer for you. Please do join us for the next technical breakfast briefing. Thanks for your time, and have a great day.